Extending a large language model's capabilities typically involves giving it specific operational rules. We do this by packaging custom CLI scripts and structured skill.md documents directly into the agent's system prompt. In an isolated test, that works perfectly. But in a real-world repository, developers rely on dozens or even hundreds of these specialized skill packages to handle complex workflows like database migrations or security auditing. Attempting a brute force approach by simply injecting every available skill into the initial prompt triggers immediate systemic failure. The token consumption costs increase linearly with every new procedural rule added to the directory. More critically, packing that much text into the prompt exhausts the context window. The agent suffers from severe context degradation, losing its grip on instructions, and deteriorating in its basic reasoning capabilities. To bypass this limitation, production harnesses like Codex and Claude Code rely on progressive disclosure. Under this architecture, the agent receives only a compact catalog index up front, stripped down to the skill identifier, file path, and a one-line summary. Progressive disclosure trades massive upfront context overhead for on-demand retrieval. It is the mandatory architecture for scaling production harnesses. This architectural shift places the burden of an active, multi-stage reasoning loop squarely on the agent. The model must first evaluate the user's request and detect if any of those brief catalog summaries apply to the current task. If it identifies a relevant skill, it must then formulate an explicit tool invocation, like calling a read file script, to retrieve the full documentation from the disk before it writes any implementation code. Finally, once that text is loaded into the conversation memory, the agent has to parse the step-by-step workflow, configure its parameters, and execute the rules. When researchers scale the library from a single skill up to 30 candidate skills, models rarely select the wrong skill. Instead, the rate of failing to select any skill at all spikes. Passive keyword matching in system prompts degrades sharply in recall. Agents often fail these tasks despite having sufficient coding logic. The breakdown occurs because the retrieval process never starts. Historically, evaluations of agents' fails relied entirely on end-to-end task completion rates to determine success. Measuring only the final output fails to isolate causal attribution. It is impossible to tell if the agent strictly adhered to the provided skill document, or if it simply solved the problem using its internal pre-training knowledge while ignoring the skill entirely. The SKILUSE benchmark solves this by mathematically decoupling task success from skill execution. It uses a 3-tier evaluation engine grounded in verifying the agent's interactive trajectories and final file system states. Tier 2 of this framework measures procedural compliance. Deterministic parsers evaluate whether the agent successfully carried out mandatory positive steps, like supplying specific CLI flags or generating required output schemas. This chart compares compliance against Tier 3, boundary adherence, respecting explicit prohibitions. Across all 8 evaluated frontier models, boundary scores 0.65 to 0.72 consistently exceed compliance scores. Language models find refraining from forbidden actions easier than executing multi-step recipes without skipping validation checks. Standard instruction following metrics cannot predict agent tool usage. Accurate evaluation strictly requires causal attribution to the explicit procedural constraints of the skill. This mathematical architecture calculates overall skill execution. The consolidated skill use score aggregates procedural compliance and boundary adherence with a 70-30 ratio. This composite score is modulated by Tier 1, the trigger gate, a binary function evaluating if the skill was explicitly retrieved from disk. If the model solves the task without reading the skill file, this trigger drops to 0. That 0 acts as a strict multiplicative gate, instantly shutting down the final equation. By forcing the final score to 0, the metric prevents models from receiving credit for lucky zero-shot completions or accidental overlaps with standard engineering practices. The trigger gate isolates the causal contribution of the skill document. A model only scores points if it proves it autonomously recognized the need for the skill and retrieved the rules. When we look at the benchmark data for the Claude Code harness, a massive performance gap emerges between proprietary models and open-weight models. The aggregate skill use scores for GLM 5.1 and DeepSeek V4 Pro collapse to 0.267 and 0.250, lagging far behind GPT 5.5.
However, re-evaluating conditional compliance isolates execution fidelity on specific traces where the skill was actually triggered. Looking strictly at those triggered traces, conditional compliance for the open-weight models jumps to 0.638 and 0.588, directly matching the execution quality of leading commercial models. Instruction following remains intact, but the aggregate scores collapse due to an abysmal 32.4% trigger rate. Open-weight models possess procedural execution capabilities that match proprietary leaders. Their failure in production agentic harnesses is driven by the retrieval initiation bottleneck. Skill execution capability is not a fixed constant of a foundation model. It is an emergent property created by the interaction between the model and the specific harness it runs in, like Claude Code or OpenAI Codex. Claude Code provides minimal prompt intervention. It places the full burden of skill discovery on the model, which actively rewards models like GPT 5.5 that possess naturally sharp retrieval sensitivities. Codex takes a different approach. It provides heavy structural scaffolding and tool formatting, which artificially boosts the discovery rates of middle-tier models. GLM 5.1 sees its trigger gate jump from 32. Equipping an agent with a skill directory can actually reduce task success rates. This scatterplot maps the consolidated skill use score on the x-axis against net task completion delta on the y-axis. A vertical line marks a skill use score of 0.50. When an agent scores below that 0.50 mark, the net task completion gain is negative. Providing a skill and having the agent partially execute it, or trigger it improperly, derails the agent's baseline heuristics. It actively breaks workflows the model could have otherwise solved on its own. To deploy large skill libraries safely, next-generation developer harnesses must abandon passive keyword catalogs. They require active semantic pre-routing mechanisms and intermediate validation gates to alert the agent when it misses a mandatory procedure. Deploying skills with low procedural fidelity actively destroys value. An aggregate skill use score of 0.50 is the strict mathematical minimum threshold required to justify exposing a skill library in a production environment.